Good morning and welcome to this talk, which will be delivered by Andrew Conn. I am Laura Stafford from the Faculty's Industrial Liaison Office. If you have any questions for our speaker today, there will be a Q&A at the end of the presentation. Please submit any questions that you have to the Q&A tab found at the bottom of your Zoom screen. This talk is part of the Faculty's Research Showcase event. The purpose of this week-long event is to demonstrate the breadth of research capability we have in engineering at Bristol to provide stimulus for conversation and hopefully future collaboration. I will now hand over to Andrew Conn, who will be talking about the soft robotics technologies for improved quality of life.
Thank you, Laura. And good morning, everybody. I'd like to show some slides this morning, but today I'd like to try to convince you how small pieces of rubbery materials can try to improve our quality of life. So I thought I would start by really introducing what are some of the major challenges we have towards our health and living in the 21st century. So certainly in the UK and other Western countries, one of the major challenges we face, and I'm excluding the coronavirus, of course, in this, is the fact we have an aging population. So the current proportion of over 65s in this country, according to the Office of National Statistics, is around 18%. And over the next 50 years, that will increase to over 26%. And with an aging demographic, a variety of conditions that require treatment include mobility issues, cancers, and things like urinary incontinence. And I think, urinary incontinence is something that can really affect people's quality of life and frankly, their dignity. How can they live in a dignified way with high self-esteem when they have urinary incontinence? So I will be covering one of the technologies we're developing to try to address that particular challenge later on. Another big challenge we face right now, especially during the coronavirus, I should add, is the fact that we're all digitally connected. So we have an increasingly digital economy and society. We're communicating online, Zoom seminars and Zoom calls and everything else. So how do we ensure that everyone has access to high-speed internet? And how can we democratize high-speed internet to make sure this isn't something that only people in wealthy areas have rather than the poor? So today I'd like to introduce a few of the examples of the research that my group are working on to try to address some of these challenges. Now, before I go any further, I'd just like to start by, managing expectations about, what I mean when I'm talking about robotic technologies. So I'm sure many of you will, in your mind's eye, already have a preconception of what a robot should do and what it should look like. Whereas what I do in my own research is look for a bio-inspired approach using soft and compliant technologies. And this is part of a larger field called soft robotics. So using soft and squidgy and compliant materials, like you see on the left-hand side of the slide there, it can have a number of different advantages. First and foremost, for many healthcare applications, is by having soft materials, it can interface with other soft materials, such as tissue in the human body, in a safe manner. It can also reduce the amount of control we need, because rather than having to contort rigid materials around a deforming soft structure, if the material itself is compliant, it will passively conform. And on the right-hand side, you'll see a pine cone, and you're probably wondering, well, what on earth has a pine cone got to do with robotics? I just shows this as an example of, some really, ingenious principles in nature which can greatly simplify the complexity of the system. So the pine cone, after it's fallen, has lots of seeds inside, and it only opens up to expose those seeds when the conditions are right. So when it's warm and has the right humidity level, that is when it opens to give the seeds the best chance of having the right conditions to grow. Whereas when it's icy and cold in winter, it stays closed to protect the seeds. So in that case, the structure itself is doing the clever stuff. There's no brain there, there's nothing else. And that's the sort of design principle which we can adopt in in robotics to try to embody intelligence into the structures and body of the robot. And that way it can reduce the amount of control and complexity in the brain of the robots. And it's something that our own human bodies, we do all the time without really realizing that a lot of the compliance and elasticity in our bodies actually reduces the workload that our brain has to do to make sure that we can stand upright and walk over uneven ground and everything else. So I just wanted to try that just to start off my presentation, just so you don't all have questions going, where are the robots? Where are the robots the whole way through? Okay, so moving on, I'd like to now go into one of the first healthcare challenges that we have been working on. And this relates to laryngectomies. So people that suffer from throat cancers, thyroid cancers, and cancers of the larynx can quite often or typically will be subjected to a laryngectomy. And in the case of a total laryngectomy, which is shown on the right-hand side, essentially the whole larynx is stripped out with a stoma that they breathe through and their esophagus directly connected to the mouth. So just perhaps to introduce firstly what the larynx is, and all of you will be familiar with the term. The larynx covers the section of our throat which has our vocal cords and also our epiglottis, and it's absolutely incredibly crucial for our well-being and staying alive, as well as our quality of life, because that's ensuring that food goes the right way, that we don't have any aspiration, food or drink going into our lungs. It also gives us our voice. And with the laryngectomy, that is all taken away. And there are some techniques that people who have had a laryngectomy can use to try to speak, but it doesn't work for everyone, and they do greatly affect, they'll never speak the same way again. And some of you may be familiar with the electrolarynx, which is a device that electronically tries to measure the vibrations. So really it has a huge impact on people's quality of life. So we've been working with colleagues at UCL. And I should say that this project called Robovox is being led by Professor Martin Birchall at UCL, who is also an ear, nose, and throat surgeon. So he actually performs laryngectomies quite regularly. And on Bristol, my colleagues include Professor Jonathan Rossiter, Andrew Heinitz, Karen Yu, and Andy Stinchcombe. Now, the approach we've taken is to try to develop a soft robotic valve. And I'm afraid I can't go into too many details with this because it's actually a requirement of our funder, the Wellcome Trust, that we have to, all our results are embargoed at the moment. This is to ensure that routes to commercialization remain open so that follow-on funding will still be available to actually drive this from lab to clinic, which is a process that could take 10 to 15 years. So for that reason, I'm afraid the specifics of our design have to stay top secret at the moment. But what I can tell you is how it works. So we have this soft, and I can say enough to say it's a rubbery, soft material we made the valve out of that will be implanted at the top of the trachea, which is our windpipe that connects to our lungs. So it will perform the function of the epiglottis to make sure that food and drink go where they should into our digestive system, down our esophagus, and that we can breathe when we need to, and also speak. So this is, critical for people's well-being, but mentioned before, also their dignity to be able to speak in the way they would like to. And the project has been progressing well, and I'm quite excited to say that we're actually doing our first live animal test next month. We've done countless cadaveric procedures where we've implanted it into dead sheep and pigs, and it will be going into live sheep next month to actually test our device what functions and is safe and everything else. So I'm afraid in that case I couldn't give too many details. The next technology we've been developing, which was led by Karen Yu, who's a PhD student, I'm pleased to say has now got her PhD, who was advised by myself and Professor Jonathan Rossiter here at Bristol. She developed a device which could help people who've had laryngectomies cough. As I'm sure you all know, coughing is a absolutely crucially important physiological function. It allows us to clear mucus and other particulates from our windpipe and lungs. And people that have had laryngectomies, because they are breathing through a stoma on the front of their throat, it means they can't really cough, because in coughing, we actually build up pressure with our vocal folds closed, and then they pop open, and that gives the really high pressure, high velocity burst to clear the mucus. So by having that removed, all they can really do is breathe heavily to try to move the mucus up. So Karen has developed a portable device with an embedded valve and a sensor. And the really clever thing that she worked on was to try to find what is the critical point that you can open the valve, because you want to build up pressure and then release it to get a good quality cough. And we did a number of tests with anonymized participants. So I promise this is the only plot I'll be showing, the only graph I'll be showing in the talk today. The left-hand side plot was with control participants, so people with an intact larynx. And they were given control of when they could release the pressure sensor the valve to open and allow them to cough. And we could measure the change in peak pressure and change in peak flow rate. And what this plot shows is everything that's above 0 shows an increase in the peak flow rate. And in some cases, they were getting 200 or 300% increase in flow rates. And likewise with the pressure, which is crucial for removing mucus. We had a much smaller participant group with people who had laryngectomies. So on the right-hand side, we had 5 participants who've all had laryngectomies. But what we found is all 5 had a significant increase in the peak pressure they could achieve, and 3 out of 5 had an increase in the flow rate. And we believe, because it seems to follow the same trend as the control group, we're very confident this device could be used to help people with laryngectomies cough. So they could essentially plug it into their stoma and allow them to remove mucus and reduce the effects of infection. Okay, so I'd like to move on to the third technology that we're developing, which isn't for laryngectomies. It was primarily developed for people that suffer from urinary incontinence. And one of the big challenges with treatments at the moment for people with urinary incontinence that need to have, where the structure of their urethra and bladder is not as it should be, and it doesn't function properly. It needs to have something implanted to support it. And some of you may be familiar with the synthetic mesh. It's often portrayed as a scandal. It's affected a huge number of women who had synthetic meshes implanted to change the tension on the urethra to ensure they don't have any leakage of urine. And many of the procedures, the tension of the synthetic mesh was incorrect, and that's caused huge problems to them. And one thing that hasn't been reported so clearly is the actual procedure and use of synthetic meshes. It was actually the gold standard procedure. It was approved by NICE and other major healthcare organizations and regulatory bodies. The problem was it was very hard for surgeons to get the right tension, because they're essentially doing it blind, through sort of keyhole surgery. And many surgeons didn't have the proper training and weren't able to do the procedure. So my PhD student, Xin-Yu Chen, looked at developing an implantable sensor that could help ensure that the right tension is there during the procedure, so that whichever technique is used, they can make sure that it doesn't adversely affect the person's health. And this sensor also has other applications. Whenever we need to be able to sense, for example, the pressure of the bladder or other parts of the body, can we have a sensor that is soft, safe, used from biocompatible materials that aren't toxic, and crucially, doesn't have any wires connecting to the sensor? So the sensor itself is a small piece of rubbery material, and it has an embedded electrical coil that was manufactured using liquid metal. So rather than having normal, copper wires, there's liquid metal, which means the circuit stays intact as you stretch it. And what that means is you could have one of these implanted inside the body. And as long as there's a transmitter coil on the outside, which we can also make out of the same soft materials, so it could be in your clothing, that's sort of indicated down here with the transmitter receiver, how much that sensor is stretched and bent can be sensed wirelessly. So it gets all its power, and the sensing signal of how much it is strained and how much pressure is on it is entirely wireless. So we're really quite excited about some of the healthcare applications that could be used for this. Okay, so that was the last of the healthcare applications I'd like to speak about. If you remember at the start of my talk today, I mentioned two of the big challenges we faced in our 21st century society. First, there are increasing number of healthcare challenges, such as urinary incontinence and cancers, such as people that need larynxectomies. And the other one was due to our digital economy and digital society. And I mean, it's hard to capture these things pictorially, but one thing we see here is a Zoom call, and we've all been doing it. We're doing it right now, of course. We all need to have high-speed internet to be able to do that. And many more companies now, it's absolutely critical that they have high-speed internet all the time. And it's been a huge priority for the government and has been investing hundreds of billions of pounds, or that's at least been promised over the next decade, to ensure that over 95% of the UK population have access to low-cost, high-speed internet. And related to that, particularly during the coronavirus, when access to shops has been limited, is rightly or wrongly, we are buying our food and our other products online and getting them delivered. I'm not here to advocate that as a way that we should be going in society, but the simple need is a lot of companies now need to be able to sort people's orders quickly and efficiently. For example, companies like Ocado have large warehouses where they need to very quickly gather people's food and vegetable orders together. So what I'd like to now present is a couple lines of research that my group are working on, which try to address these challenges, which can affect our living in modern day society. So the first relates to high-speed internet. And we're working with BT with this project because BT are committed to install high-speed fiber optic cables to an increasing number of properties around the UK. I said before, ideally over 95% should have high-speed internet. And the big challenge they face at the moment is the fact that they have to dig up troughs. So if they want to, for example, lay a fiber optic cable underneath the road, they need to dig up a trough that closes the road to traffic and sometimes even pedestrians. And it's very laborious and costly and so on. So what we're working on is an underground robot that can dig underground to lay the fiber optic cable. And you can see a schematic of the robot on the left-hand side here. The principles, well, actually, in terms of the concept, quite simple. We have rotating augers, which can essentially drill through the soil. And within the robot, we have a compact 3D printing system that can print a plastic duct. So the robot will dig underground, avoiding infrastructure and drainage and other things which are embedded underground, and then rocks, of course. And it leaves as a sort of tail this 3D printed duct that's completely clear. And once it's done that, the fiber optic cable can then be fed through and connected to the premises. And I'm sorry for the acronym on the diagram on the right-hand side. FTTP is fiber to the premises, which is the big aim. And I'll quickly jump back to stop sharing just because I wanted to show, I'm afraid I don't have any nice pictures of the robot. This project has been heavily affected by coronavirus of last year. So we were doing lots of tests, essentially improving the shape of the auger. What I do have is an example of the 3D printed duct. I appreciate it's just a tube, but just to give you an idea of the scale. And what we did do early last year was test the strength of this duct. And we're really pleased to find that it could withstand over a metric ton of pressure. So we're very confident that once the duct is printed, for example, under a road or elsewhere underground, it will be able to withstand the pressures and forces and remain intact, which is also related to this digital economy. As I mentioned before, companies like Ocado, in fact, almost all the supermarkets, Amazon, lots and lots of suppliers now, they need to have an online presence. They need to be able to receive orders online and deliver them in a quick and efficient manner. And what my group has been working on is a soft robotic gripper that's able to handle delicate fruit and vegetables. And the key thing that we've tried to do is to minimize the control complexity. You know, for you or I, picking up a banana or a tangerine, we could do it without thinking. But if you have a robotic manipulator, so a robotic hand that's made out of rigid materials, it's actually a very complex control problem because the robot needs to, you know, judge the shape of the object. It needs to judge the texture. How soft is it? If it squeezes too hard when it picks it up, will it damage the fruits and vegetables? You know, it's a very, very multifaceted challenge. So what we've done is used a very soft material, and this is a pneumatically driven gripper, where the fingers themselves are very soft. So when you inflate it, they will comply to the shape of the object. And this particular design, the fingers splay passively. So you can effectively just press the gripper onto the object. The hand will passively conform around it. And all the controller needs to do is turn the pump on to pressurize the gripper and pick up the fruit or vegetable. And I've got an example of one of the fingers here, which I'll show in just a moment. But the bottom of the slide is just some very recent work we've done where we developed a completely soft pump, because we're looking at increasing the complexity of these grippers by embedding more pumps. And we can actually now have a soft pump that's embedded within the gripper. So a fully soft hand, essentially, that can be activated by an electrical signal. So I'll just quickly jump back to my camera just to show one of the fingers. I haven't got the pump with me, I'm afraid, but I just wanted to show you just how soft and flexible this is. So the nice thing about that is it's really hard to damage these. You can hit it with hammers, and probably the one thing it's not so robust to or anything very sharp. So if you take a needle, you can puncture it quite quickly. But that aside, when we pressurize it, you can see it can curl quite nicely. So that hand I showed on the slide was basically multiple of these fingers. When it's pressurized, it grasps around the object. And because it's soft and compliant, it will conform to the shape of the object it's gripping. I appreciate it's been jumping around between health and living, but I just wanted to show the breadth of applications that we can try to address with new types of robotic technology. And just to finish my talk, you know, in terms of future directions, for that last example of the soft gripper, we're looking, I mentioned the embeddable soft pumps. We're looking at more complex structures, for example, tentacles inspired by the octopus, which could be used to grasp objects or for inspection or other applications. And in the healthcare domain, we don't just look at implantable devices. We're also looking at wearable technologies. But one thing we've come to acknowledge in our collaborations with clinicians and surgeons is what they will tell us is you can develop the most amazing implantable technology, and particularly if it's for a more elderly demographic, it needs to be able to be implanted in a minimally invasive procedure. Because if you want to help somebody with urinary incontinence who's in their 80 years old, the risk of going under a general anesthetic and having a very invasive procedure could outweigh the benefits of improving their quality of life. by reducing the urinary incontinence issue. So that's something we've been looking at trying to make technologies which can be implanted in the most minimally invasive way. And with that, I'd like to thank you very much for your attention and for listening, and I'll be happy to answer any questions.
Thank you very much, Andrew. We have a question from Simon, who is asking if you're involved in the Pipebots project.
I'm not. Though, interestingly, my collaborator at BT was aware of the project, and often the sort of 6 degrees of separation. A company they collaborate with called Synthetech, who they introduced to me, they're working on the Pipebot project. So no, I'm not directly involved, but my colleagues in mechanical engineering, I think, are doing some really exciting research with that. I think it's showing perhaps different angles where we're coming to, related problems.
Thank you very much. I've got another question for you, which is, where do you want your research to be in 5 years' time?
Oh, what's a notoriously tricky question. One of the main things that we want to do, particularly with the healthcare technologies, is, and I mentioned, going from lab to clinic typically takes about 15 years or even more for implantable devices. And we have a certain number of milestones along the way. So certainly, I mentioned we're doing live animal tests next month. In 5 years' time, it'd be really fantastic to know that we've learned enough from that, and then the tests are successful, that we're able to continue working on implantable devices. And otherwise, it's a case of just making sure that we can continue to develop robotic systems that don't just sort of work for us, but also can work with us. I think it's something we need to consider, that we don't want to completely eliminate, manual labor altogether. In many cases, we can have devices which can, help reduce back pain by giving us more support if you're lifting things. So I think that sort of augmentation aspect is something I'd like to try to push my research over the next 5 years.
I'm sorry, that had to happen at some point. We've got a question from Sophie, which is, in terms of healthcare, do you work on the patent side of things? I.e., how open are you to patents to these interventions?
So the large project we're working on with UCL, the Robovox project for the artificial larynx. With that, we've been having discussions over the last year, and with multi-institution projects, it can also be a challenge making sure that everyone is on board with the direction of these things. But for our technology to ever have any chance of actually being used to help patients in, say 10 years time, we do need to make sure those commercial aspects and IP is in place. So yes, we are looking into patents and other protection.
We have another question from Simon. How much more potential is there for bio-inspired ideas for robotics?
I think there's still considerable potential, particularly when we start thinking about, rather than just trying to copy, for example, making a robot that whatever walks like a dog or whatever else it might be, and actually try to dig deeper into what are the fundamental principles of those biological systems. So the reason I chose the pine cone, it's a really simple structure, but actually the principle of completely disembodying all the control from the brain, putting it into the body rather, is a very powerful thing. And that's something we're looking at actively, is what other examples can we take of where we can embody intelligence into the structure and body of the robot.
Brilliant, thank you. And to go back to the question from Sophie, I completely misread it. If we look at healthcare, do you work on patient side of things as well? And how open are you to interventions on the patient side of things?
Generally, I'm quite far removed from that, from speaking with patients. In tests where we do speak to user groups, but generally most of the technologies I'm developing, especially the ones which are implantable, it's going to be a number of years till they're ready. but no, we do actively engage with clinicians and nurses and user groups. And it's also very important to make sure we actually ask people, we can show them some amazing technology that you apply 2 volts and it can deform and everything else. But the first question you get is, can I wash it? Or how will it look? Those sorts of things, which as engineers, you sometimes forget about, that actually the usability of something can, the demands can be quite different. So that's why it's really important to engage with potential patients.
And how would you like to work with industry in future?
I've certainly, for example, the ongoing collaboration with BT on the duct printing robots, have really enjoyed that. I think something which, as part of the relationship growing in that example, is we are trying to sort of break down the, it's not just us staying in our lab and our industrial partners staying remotely, and then every few months we give presentations. They've opened up test facilities and they've actually invited us to come and try out our devices there. So I think, a slightly increased integration where relevant is something which I think could be really beneficial to both parties, because we understand their needs more and they also understand the technologies much more.
Fantastic. I think we've covered quite a bit of these things, but how do you think industry can use this research, or how do you think that relationship can work?
I would say, certainly for, I'm sure majority of people from industry attending this who won't be in the healthcare domain. I think one of the main or potential benefits of the sorts of technologies I've presented today, which I didn't really have enough time to go into any detail, is by using more compliant materials, we can develop technologies which can deal with uncertainty, is really what I was trying to say. So when I mentioned about simplifying the control aspects, it's possible to have things like the gripper I showed, which needs minimal control, but you can put almost any shape or object in front of it, and it's able to pick it up. So I think this is a direction we're definitely moving in robotics, certainly in soft robotics, which could be beneficial to industry, is in any applications where there's lots of uncertainty, whether it's, I said the shape of objects or different other aspects of the environment. Sometimes you have visibility, sometimes you don't, if you're working underground or in pipes and other dark and dirty environments. So I think that's one area that certainly I'm very keen on working on, and my group too, and more generally in soft robotics, is systems that can deal with uncertainty in real world applications.
I think we've got a note from Harriet. If any of our attendees have a question and you would like to raise your hand, please feel free to do so. Andrew, following on some of the questions that we've had on the presentation, are there any other comments that you'd like to add around your theme?
Nothing in particular. I think I did skip my very last slide, which had my contact details, but I think if any attendees had any further questions, I'd be happy to answer them by email, and likewise, any of you that want to see more of the technical details, the research papers are all available, open source on the Bristol website, and I can point people in direction or share the paper with them directly.
We have a question from Marie Rose. Where intelligence is embedded, are actions predictable, or will there be unpredictability in them like an AI robot? That's
a very, very good question. And that is one of the central challenges. If you completely remove the brain in your robot and you're relying entirely on the passive responses of the body, how do you ensure that is actually safe? Because you've lost an element of control there. It really does depend on the application. And in truth, the kind of optimum, and much like with the human body, is you do still need that centralized controller. So it's able to, and that can be where AI comes in. It is still making those safety critical decisions. But by allowing a lot of these sort of low-level responses and control being done by the body, it reduces the computational workload on the brain. So for example, rather than having to do all the processing through a camera, eyes, if a lot of the kind of low-level stuff's being done by the body, that means the brain of the robot can concentrate on those safety critical aspects. So I think having the two working synergistically is key, really, to ensure that it does remain safe. But it is a good question, and of course in robotics, as we put robots more and more out into the real world, these are increasingly important questions that we need to answer.
Brilliant. Thank you very much, Andrew. This brings the session to a close. Thank you all for attending and for your questions. I'd also like to thank our speaker, Andrew Conn, this morning. In the current climate, online is the only way we can really do this type of event, and we appreciate it's not as interactive as we'd like. If what you have heard today or throughout this week has captured your interest, please get in touch with us. Our Industrial Liaison Office is here to connect you with our academics and students, and contact details will be sent after this event. So in light of that, I would like to thank everybody again for joining us, and for Andrew for presenting this morning, and I'd like to say goodbye.